Hello everyone, my name is Henrique Mayago. I am a power electronics and hill test engineer here at Typhoon HIL, and today I'll be showing you this overview of our test framework and some of its features. To get started, I would like to just show a couple of images to give this overview of how it's structured. So we use Python to develop our API to control the HIL, and that's why we chose PyTest as our test runner for the test automation solution, and also for showing the results we are using the DLO report because it's well integrated one to the other and they work very well in Python. For writing the tests, you can have all your tests implemented that will be using all these boxes here. So you can use the TyphoonTest analysis functions that will allow you to very easily and quickly evaluate how a signal is performing and if it's meeting your criteria. You can also use our unified API to control our equipment, and you of course have access to all Python libraries that you can use in this framework. In order to make the test more generic and be able to easily change the environment where we are running and also the device in our test, we are using drivers to interface with those. So on the environment driver, it's where we are sending the commands to in this case to the HIL, but you can potentially change the environment to be, for example, the lab, so you could run the same test in the lab. As for the device under test driver, we are using that one for sending commands to the device under test. So let's say you have two product lines that behave similarly and they should run as the same set of tests. You don't need to rewrite your test. You only need to select a different driver and connect that controller that you want to test. Since this is all code, it's very easy to use version management control software in order to track all the changes. Here just have a snapshot of how you could structure your test folder, so you can organize them by folders. For example, here we have some tests for grid-tied converters, in power tracking, or for grid support capabilities. By doing this way, it's very easy to keep your tests organized and select which one you want to run at a given time. Also, you can have all the drivers for different manufacturers, different environments, all in the same place, and this way you can select which one you want to run at a given time. At this demo, I'll be showing you results that we collected from this test rack. So here we have the server where the software will be running, and the Typhoon Control Center software will be running, and is connected to this HIL box and also to the device under test. So in this case, you can see we are only using one of the control boards here, and this one is directly connected to the PC, where we can read some information directly from this device. Just an overview of this test automation stack. So here in red is what is on-premise, so what's on that rack there, and in blue we have everything that can be on the cloud. Just to be clear, you don't need to implement all of these at the start. You can start by just running the test automation on your PC that's connected to the HIL and the controller. So you can run those manually, and you are going to have the results only on your machine. But here the idea is to have end-to-end test automation where you can make changes to the code and it automatically runs checks if everything is okay, and you have the reports available. So here, just to have a different perspective to see who would be using each one of these software. So for project management here, we are using Jira. For project management, for test management, X-Ray. These two can be changed according to your needs. For the test and firmware engineer, so they will be using, for example, GitLab for storing the test code and also the firmware code. For the continuous integration, we are using Jenkins. So in Jenkins, you can set triggers to automatically start test execution. So you can make it run overnight. So every morning you have the results from the most up-to-date tests and firmware. You can make it run on weekends with more test cases, or you can even trigger on every push you make to GitLab. You can start the test execution, so you can see if you broke something that you didn't expect. You can see that very quickly, and you can fix that issue as soon as possible. You can also have access to the alert results on the cloud, so anyone that has access to this server can see the results. And all this part in red here, it's automated, so you can set the triggers on Jenkins and everything is going to run automatically and generate the report. Just the flow of how it would work. So the manager would define the tasks, the test and firmware engineer would schedule when it should run, write the code, all the execution and test collection is automatic, and then the test and firmware engineer can examine the results and see if it's implemented correctly. All this data can be then summarized automatically and populate the project management tool, so the project manager can be up to date and always see what's the progress of the project. So now I'll be going over a little bit of the code, so you can see how a test actually looks like. So for this example, I'll be showing this power tracking test. So at the beginning, we are just importing some libraries, the test configuration, the drivers for the device under test and the environment, some functions to use during the test. And here we have some functions from our API. I'll just be showing some functions to compute the RMS value of a sinusoidal waveform in this case. Also for checking if a signal is constant, and this step info is a function that will evaluate the metrics of a step response, like settling time, overshoot, undershoot, and things like that. Here, so it's the test itself, and I'll be showing two ways that you can summarize the data. So you can use this one that will show the summary for after each test case, or you can break this down and have one test that's just for showing the summary results. So you have a lot of flexibility on how you want to show the results. And here on the test itself is where we define the test procedure. So in this case, what we'll be doing, we'll be changing the grid, we'll be changing the DC bus voltage, sending a command to the device under test to change the power reference, getting the data and analyzing it. And here you can see one of the very nice features about PyTest. That's how you can parameterize those conditions. So you do not use for loops. You use these markers where you can, for example, here we are setting different power references and also grid conditions. So it's going to run for all these conditions that we are setting on our parameters file. The one very other nice feature about using PyTest are the fixtures. So this is one of them that will be collecting test data, and the other ones is that before running the test itself, before being able to do this, you need to set your converter to nominal condition, and you also need to set it up. So here is the fixture for returning the converter to nominal condition, and here is where you'd set up the device. One nice thing about fixtures is that you can define what's the scope, and this will let the test runner know when you want these fixtures to run. So let's say for the test, power tracking test, you want to return the system to nominal condition after each test, because if for some reason the controller gets unstable in one condition, you do not want that to propagate to the next test. So here this returning to the nominal condition will run after each test scenario. But setting up the system, you don't need to load the model and start the device under test every single time. So you can define that this operation will run for each module. You can even change the scope to a session, so this would run just once for the test session. Going back to the test itself, so here's what I mentioned before about this abstraction layer and using drivers. So for the environment, when we want to change the grid, we are using these functions that are very easy to understand. So when you read the test code, you know what it's supposed to do. So we are passing the nominal voltage and frequency of the grid that we want to change. Also change the DC bus voltage. Here, since we need to be aware of the power capability of the device under test, so we are curtailing this reference power to one that the converter can actually produce. And this will be important on the test results. I'll be showing that I am here expecting that the converter is curtailing the power, keeping constant power factor in this case. After that, you can start the capture. So here we are capturing data both from the device under test and from the environment. We are here again using the abstraction drivers to change the power reference of the converter. So here you can see we are just passing these two values, and actually the way this is implemented, we are sending a can command, but having all that code here would just make it more difficult to understand the test procedure itself. And also when we wanted to change from one device to the other, let's say the other one uses Modbus, you'd need to be changing the test itself in order to be able to run the same test for different devices. And here, by using the drivers, if you just change the driver underneath, you can run the same test for these two conditions. After we do this, send this changing power reference, we can capture the data both from the environment and the device under test. We can use some TyphoonTest functions to merge these two data sets, data frames together. Here is where we are using the window RMS function to compute the RMS for the phase A grid current, and also the analysis functions. So here we want to see the step response of both the active and reactive power. We have some conditions that we can specify. We can also check if the active and reactive power, they are constant. So this is also analysis function that we have from TyphoonTest, and all of these will be generating some plots in the report automatically, so you don't need to spend any time writing code for generating plots for these very common situations. So here we are also checking the state of the device. So we collected the data from the device itself, and we are checking if the state is the same throughout the whole test. We can add some custom plots to the report. We can summarize the data that we want to show in the summary, and do the final assertion where we are checking if all this criteria is met. So now that I have given you this overview of the test code, I want to show you how this would look like in the report itself. So for the test report, we can access that in the cloud. So here's the Jenkins server. So we can sign in. You can see all the different jobs. So each one of these jobs has a different purpose. We'll be looking at the one that is running all of the tests. You can see here at the right, there's a trend. So you can see how the history of all these test conditions, how many tests are passing, how many are failing. And you can also open, I'll be opening this last one, so you can see how the report looks like. Here is the overview of the test. So we have 113 test cases, and it passed 55% of them. You can see how many you can open and take a better look at each one of those, and you can also see how many test defects you have. So when you have an error occurring in the test, you can also see it here, and you can identify it and fix it. Let me go over this power tracking that I showed you. So here we have the summary and all the test cases. You can see all of them here. Let me open this one so you can take a better look. You can see all the parameters that you set. So here you have the DC, bus voltage, the grid frequency, the grid voltage, and also the active and reactive power reference that you want for the test. All the fixtures will be in this setup, and here is everything that's in the test itself. So in the fixtures you can open and you can see if everything that happened before the test. So as I mentioned, the first stage is to set up. So you can open here and see how the HIL was set up, how the device under test was set up. So all this information is, most of this information is being automatically generated just from using the TyphoonTest API. So you can see if you loaded the correct model, it loading the desired file, some of the hardware settings, loading the initialization file. Everything is logged here, so you can see if you had the correct files, if something is odd in your test results. Also for setting up the device under test. Why I mentioned most of these are automatically generated, because you have the freedom to also add some custom information here. So for the device under test, since it doesn't use our API, you can add custom information here. So for example, starting the CAN readings, starting some periodic messages, you can add this as you'd like. So for the test itself, as we saw, so first we are changing the grid. So here's all the steps for changing the grid, changing the DC bus, starting the capture for the device under test, starting the capture for the HIL device. All the parameters are shown here, so you can track what was happening in the test, waiting some time, changing the power reference to these values, and getting the results from the HIL. So this is an API function that is gathering the data and generating plots for every single measured value, so you can open it and see how it performs. So this is automatically added to the report without you having to write a single plotting line of code. Also getting the results from the device under test. So here you can see the state was always equals to 2. Resampling these data frames, computing the RMS of the phase A current, and I have put all the test information under this drop-down menu. So here you can see those 2 step infos and checking those 3 signals if they are constant. So here we have the step info information about the active power. You can see the results numerically here. Look at them, or you can see it graphically. So in this graph you can see the response of the system. So here is you can see the undershoot, the rising time, the settling time, also overshoot. Here, since the ripple is very small, it's not possible to see, but you can also have information about the ripple in this steady state condition. We have a very similar result for the reactive power. Here's the plot of this step response, checking if the active power is constant during the last 50 milliseconds. So this is in orange is the region that we allow the signal to be within. Since it's inside this region, it's passing the test, the result is true. Same for the reactive power. So here we are expecting the response to be 98%, so it's the strictness inside this region. Since it's outside, it's failing the test. And we are also checking if the state of the converter is always 2. In this case, 2 means that it's in nominal state. And for adding additional information to the report, it's possible. So here you can add some custom plots, for example, just adding all of those results in a single plot, so it's easier to see what's happening. So for active power, reactive power, the envelope of currents, voltages and currents, and also the state. So here is the capture for 5 seconds. You can also have the same signals, but now just looking at the last 50 milliseconds and see all the currents and voltages. Here's what I mentioned before, that you can have the summary results in different fashions. So this one, you can have it, all of them have this summary here, or you can just to make it easier to find, you can have one test that shows only the summary, and all of them will have this summary custom image that shows the summary results of all these tests. So here is the test condition with the grid voltage, frequency, and DC bus voltage. The black X is the test reference. The blue X is the expected value. So as I mentioned before, we were expecting that the power would be curtailed using constant power factor, but in this case the controller is prioritizing the reactive power. So here is where it ends up in the actual test. So since it's not passing the test, it's red, and here is a condition where it's actually passing because it's very close to the expected value, so we have this green value here. So this would be the overview I would like to show you today. Thank you very much for your attention. See you next time.